Yeah, so let me just quickly clarify. I'm not using bootstrapping in like the technical sense of the word, just referring to the fact that we were able to get a compiler project off of the ground, I think, relatively quickly using Yule. So that's all I mean there. And yeah, my name is Grant, and I work on this Feeling project with 3 others at the EF. All right, so a quick overview of Phi. It's a high-level smart contract language. The compiler is implemented in Rust and it targets EVM. And we currently use Yule as our IR. And yeah, so I'm not really going to be talking about the language too much, so just kind of get a look at it and just regular high-level features. There you go. And now a quick overview of Yule. This is a lower-level language. You can write smart contracts in it. It's not as featured as a high-level language, but you can still do everything in it, and it retains a readable property. Humans can just read this. I added in the token contract that they have in their documentation. I don't know if anyone can see this, but yeah, let me just go over this. So it provides functions and data objects, basic control flow, and that's all you really need to write a contract. You have a runtime object. You have things like string literals as data objects. You have a dispatcher as a switch statement, and yeah, you have this initialization code up here. So you can look at this and read it. So as far as a high-level smart contract language goes, you want more features, so you want to have ABI encoding and decoding, you want to have call dispatching, you want to have special statements like event emits, revert statements, you want to have type-specific functions like contract creation, contract construction, or type constructors, things like that, and you want to have storage fields. So these things are not provided out of the box with Yule, so you need to, during code generation, add support for these things. And this presentation is just going to be about how we do that technically. Yeah, so as far as the bulk of it is just adding all of these runtime functions for everything you need, and then just mapping user statements to use these runtime functions, and do the encoding and decoding, call dispatching. Yeah, so the 3 things are standard runtime functions, so like math stuff, like very simple ABI encoding and decoding functions, memory and storage access, things like that. And then you have these analysis-based runtime functions, so things that you can't just add without thinking about. So these are more complicated ABI encoding and decoding functions. Event emit stuff, reverts. These are things that you need to perform analysis on the source program and then decide what you're going to add. And then you generate these functions and you add them. And then you need to map the user-defined functions and then add the dispatching. So this is just kind of everything you need, and then we just batch it all together and add it to the runtime object. So as far as how we actually do this, we use some tooling. We use this Wuerker crate, which was originally written by Axic, and we forked it. You can find it here. When we picked it up, it had most printing. It had all the types you needed for a UL AST, and then we added these shorthand macros. So when we're building the runtime for a contract, it's a lot of code that you need to generate, and you need to manage that complexity. So as opposed to just writing AST objects by hand or putting strings together, we're using Rust or declarative macros in Rust. And just show of hands, do people know what declarative macros are? Okay, cool. Okay, so declarative macro is just a feature in Rust where you're able to define a expansion on some tokens. So you match a set of tokens and then you expand them, and you just use it to simplify the code you're writing. So what we've done here in Wuerker is we've defined declarative macros for every AST node type. In this case, we have a function definition, and we're basically just writing Yule by hand, and then adding in an instance that's known at runtime, and just expanding this into an AST object that would span, it would take 50 lines or so to write. So this is extremely useful. Yeah, okay, so right here, just demonstrating how we build up the standard runtime functions. We just, grab things like this function right here. This is a math function that we just add by default. And then, we have the same thing with data, some ABI functions, revert stuff, and some contract stuff too. We just put it all together, and then we return it in the standard set of runtime functions. And then we have the more complicated stuff, like decoding. So like here we have a function which generates a UL function based on like for decoding a uint based on where it is. So it could be in call data, it could be in memory, and then also the size. So we just pass these things in, and then it builds up the entire function for us. And this is just batched together with a bunch of other stuff. We throw it together, and then it just gets baked into the runtime like everything else. Yeah, so the last thing you need to do is map all of the user functions and then create a dispatcher. So again, we're just using macros here. So switch macro to generate a switch statement. This is the dispatcher. You have all of your public functions. Those map to arms. Here, this syntax right here is inserting a set of switch arms or cases, and then just telling it ... You're getting an iterable set of these, and you need to expand that. Yeah, so that's everything that you need for contract runtime, and then we need the contract initialization. So again, we're using code macro to write the contract initialization stuff. So we have the init function, that call graph, all the functions that it calls, and we have all the decode functions that you need. And then we're just writing more UL code, copying the parameters into memory, and then decoding them, calling the init function, and then running the deployment stuff. So now we have a whole contract. So we've gone from say like guestbook to a long, UL contract. Yeah, so once we have the UL AST, all we need to do is hand it off to the Solidity compiler, and then it just compiles it to bytecode for us. And the UL compiler, you can just opt into optimizations. Which is quite nice because that means that we don't have to think too hard about the function that we generate. We just kind of give it a ton of functions, and if it doesn't use anything, then it just gets rid of it. So and it's reasonably gas efficient. Harry, I think is doing a presentation on UL optimizations after this. I'm not sure if it's UL though. Yeah, so I guess just a few remarks. UL has made it pretty easy to implement a high-level language. Overall, it's pretty well documented and easy to use. If you ever have any questions, you can just go to the documentation, and it's pretty clear as to how it works. One of the downsides is that we have to compile in Solidity into our compiler, which adds a lot of build time, and then also, sometimes things break because Solc has a number of system dependencies, and that can cause problems. So ends up adding a lot of time that wouldn't be spent if we were using a Rust native backend. And like over time, kind of our goal is to replace a lot of this runtime generation code with fee code. So this is kind of seen as a crutch to us, but we want to have high-level features right now, so we just do it. And the UL optimization step makes things a lot simpler. So that's it.
when you mentioned that you're gonna gradually replace YUL runtime with Alfie code, that means that you're gonna also stop compiling to like YUL as or AR. Is
No, I
gonna
mean,
compile down to bytecode, or you're gonna still use YUL as
I mean,
AR?
that's not really like a consequence of that. We just want to remove compiler complexity. So like, like we're currently like adding just functions during UL cogen for like handling event emits. I think ideally we would have emits and events defined strictly within the language. So like, right here that you see like this, where is it? Yeah, emit signed context book message. Like this could be ctx dot emit, and then you're passing in, signed a signed event. And like if we wanted to keep like special event, like a special syntax for event definitions, that would just be lowered into a struct. So this is kind of like how we're thinking about things. But doing that requires, a list of features that take a while to implement. So we're just kind of taking like a shortcut in some cases, and that's what I'm saying here, which is that like the YUL runtime generation, a lot of it is just kind of like a crutch, but it works.
Great, thanks.
Do you also do like other compile time checking that isn't included in YUL? Like a static checking step before the YUL translation?
Yeah, I mean we do analysis beforehand. Yeah, I mean make sure that we do like specific like type checking. Yeah, we do
like
all that
extra,
stuff.
because you've got new types and things. So
Yeah. I mean we have like a whole analysis crate, and that's just kind of like, that'll just stand on its own for a while. Yeah,